So, hi everybody. Let's restart this astroparticle physics course. And then, if you remember last time, we had a look at how the universe works, how it expands. Then we had first exposure to the notion of dark matter, right? What did we do? We write some equations for a soup of gas of galaxies governed by Newtonian dynamics. You still didn't catch me, right? I propose those who go to the general relativity course to try to catch me where I'm wrong. But, well, so far so good. So then we wrote a couple of equations, like this was a consequence of energy conservation equation. In cosmology and general relativity, it is called Friedmann equation. Then there was an energy conservation, first law of thermodynamics, which is in a sense also energy conservation or stress energy conservation in terms of general relativity. Then there was equation of state. We can solve this system of equations one way or the other to see what is the dynamic of the universe. But the first measurement that we can derive from this general picture is that today we measure the expansion rate of the universe. It is called Hubble parameter. And this gives us a possibility to estimate the density of the universe. And it was too high. It was ridiculously small, something like 10 to the minus 29 gram per centimeter cube. But by astronomy standards, it is very high. If we average over the volume, the density of matter in all the galaxies, we find that a mismatch by a factor of 1 or maybe 2 orders of magnitude. Then we tried to imagine, what can be. Well, this means that the universe is filled with invisible matter, dark matter. We tried to see what can be this invisible matter. And, well, our first guess was why not to try with neutrinos. Then we understood that at earlier times, somewhere, well, during the first second of existence of the universe, let's say, then right after the Big Bang, the neutrinos were in thermal equilibrium with the rest of matter in the universe. So then, as a consequence, today we have a cosmological background of neutrinos. So all the space around us is filled with neutrinos with density about 100 particles per centimeter cube. These particles, obviously, we don't observe them. So in a sense, they are dark matter, right? The only problem with neutrinos was that they are too light. If we want to provide this 10 to the minus 29 gram per centimeter cube, we would need neutrinos with rest energy of about 100 electron volt. And this is not the case. We know that neutrinos are lighter than 1 electron volt. So it didn't work straight away with neutrinos. As a byproduct, we considered a possibility, well, we discussed that people are working on detection of this cosmological neutrino background. Still, since it exists, it's interesting to measure it, even though, well, it is a challenging thing because the cross-section of neutrino is ridiculously small, so it escapes whatever detection, yeah? But there was a way to do this with, this is called induced beta decay, right? So I put these cartoons as a reminder of what was at the previous time. And today, what we will try to do, we will try first to patch this failed model of dark matter with neutrinos. We will try to consider a better neutrino, in a sense. And then we will try to see if we can test this hypothesis, that the dark matter is made of better neutrinos. Before going really for tests of this hypothesis, I will present you some complementary evidence of existence of dark matter which we get from astrophysics, right? So that's an ambitious plan for today. So let's try. Maybe. Yeah, I come back to this. No, I come back to this. This is a reminder from previous lecture. How did it work with neutrinos? We told that in general, neutrinos participate in, well, interactions involving weak, with other particles through weak interactions. Then neutrinos can be converted into other particles, and other particles can produce neutrinos. This happens in the universe as long as the time, maybe since before next interaction, is shorter than the current age of the universe, right? So neutrinos have a possibility to interact at least one time in the history of the universe, right? So the interaction time was given by this estimate. I take, well, the interactions are characterized by a cross-section. It's the size or area swept by the particle when it goes through the medium. As in this picture, this would be the surface of this ball, right? So any particles that I'm starting to mix because yesterday I was teaching in French, so I'm still thinking in French. Yeah, that's interesting. So I'm now translating from French into English. That's peculiar thing. So any particle that finds itself on the way of this particle that I am considering would bump into it, and then there would be an interaction, right? So for neutrinos, the interaction is known. For those who go to particle physics course, you will see that it's given by this formula. The neutrino interaction cross-section depends on energy. That's one thing to know. G Fermi is a fundamental constant. Then we can find the mean free path, or the way till the next interaction, right? That would be 1 over the cross-section times the density of the medium. And you notice I use the system of units where the speed of light is 1. So I don't distinguish between seconds and centimeters, right? I can always convert time into distance by referring to what is it, the time that photon would take to travel to that distance, right? So I can convert in time before next interaction, and then I would compare it with the current age of the universe that I estimate as Hubble, this parameter, this thing r dot over r at the current time of the current moment in the history of the universe. And you notice I use this Friedmann equation from the previous page. I take square root of it. 1 over this would be the current estimate of the current age of the universe, right? Called Hubble time. So I compare the two time scales and I find the moment when the two time scales are equal. And then this gives me a temperature, estimate of the temperature at which neutrinos stop interacting, right? Since that temperature, that was about 1 mega electron volt or 10 to the 10 Kelvin. If I would not use, again, I'm using units in which also Boltzmann constant is 1. So I'm measuring temperature in electron volts rather than in Kelvin. So at the temperature about mega electron volt, neutrinos stop interacting. And since that moment of time, nothing happens to them except for the fact that their density is diluted because the universe is expanding, right? So their density goes as 1 over the size of the universe, or we are rather talking about scale factor because, well, whatever size increases, right? So it goes as 1 over scale factor of the universe to the power 3, right? Like 1 over the volume. That was the history of neutrinos. And then based on this calculation, we make a quantitative prediction about this 100 neutrinos in every centimeter cube around us, right? So let's try to imagine another particle that is almost like neutrino. It participates in weak interactions, so it would have all these reactions like listed above, but it is more massive than neutrino. Let's be bold. Let's imagine that the particle is so massive that even particle collider in CERN was not able to find it. So there, what people are doing, they are colliding particles with energies in the tera-electron volt energy range, right? And then they look if there are new particles of lower energies produced. So they are sensitive to particles that are maybe 100 giga electron volt rest energy or something. So we are talking about very heavy analog of neutrino here. Otherwise, perhaps a particle with lower mass would be noticed in particle collider experiments. Yeah. Even if this particle is weakly interacting, you know that in particle collider experiment in CERN, they never detect, for example, neutrinos. They only know that there was a neutrino produced. Why is that? It's weakly interacting. It doesn't like to be noticed, right? So the cross section is small. Typically, when there is a particle collision at LHC, neutrino is produced, but it goes through the whole detector without interacting, right? In fact, it would go through the whole Earth without interacting once even, yeah? So how can we notice this? How can we understand that there was a neutrino produced?
Charge conservation.
Charge, maybe charge, right? Because neutrino is charged with respect to weak interactions. An easier way would be to see that if we check energy and momentum conservation, we would see that something doesn't work, right? There is some missing energy or missing momentum. That's how people know that there were neutrinos that escaped from the collision, right? So the same would be for this would-be analog of neutrino. Even if it's not detected in collider experiments, people would notice that something is wrong with the energy conservation, right? That's the idea. So, but still, if we would take a particle that is rather massive, the probability, well, the energies of collisions would be typically not sufficient to produce these particles. That's how it would even avoid, well, this indirect signature of, well, it's never produced in collisions, right? If it's very massive. Okay, then, so how would I modify the calculation, the previous calculation for this very massive analog of neutrino? Try to follow me. So I still want to use this formula for time before next interaction here. Although now when my particle is very massive, it may happen that by the time when it decouples, it is already non-relativistic. Neutrinos well, they are low mass particles, so they always go with the speed close to the speed of light. If my particle is non-relativistic, I start to distinguish between mean free path and time before next interaction. I would not convert mean free path into time using speed of light. I would convert it using the velocity of particle itself, right? So my time before next interaction gets one extra thing here in denominator. If you think cross section is something that is measured in centimeter square, it's an area, it's area, right? Density is number of particles per centimeter cube. So it's 1/centimeter cube. Then sigma times n has dimension centimeter. If I want to have time, I divide by velocity, so that's good, right? So I have something that is measured in units of time. So this would be my time before next interaction, and I compare it with Hubble time again. So I would extract this h from Friedmann equation and, well, express Hubble time as 1/h. Yeah, the idea is the same. Now, when I, well, in the case of neutrinos, the density. Neutrinos were relativistic particles, so their density temperature relation was the same as for photons. Photons are gas of relativistic particles. Neutrinos are gas of relativistic particles. So for neutrinos, I used an estimate of the density like this, 1 over T to the power 3. There was some sigma Stefan Boltzmann times something, but I let it out, yeah? So for them, the temperature was, the density was proportional to temperature to the power 3. For non-relativistic particles, the distribution is different. It is called Maxwell-Boltzmann distribution. In thermal equilibrium, I don't know, you have seen perhaps this form, right? So I would use another formula for density. That is non-relativistic limit of the Planck distribution, by the way, yeah? So then this is one modification. I would put the density like this here. And for velocity, by the way, I would put something that is expressed through the temperature, because I know that the average kinetic energy of particles is given by 3/2 K Boltzmann T, yes? So the formula on the left would change by a little bit. You follow me? So I plug all this stuff into the left-hand side. This gives me this combination. And yeah, this is 1 over the cross-section. This is 1 over velocity. This is the Maxwell-Boltzmann distribution. And I can reduce a little bit what I see here. I see temperature to the power 1/2, temperature to the power 3/2. Overall, it gives me 1 over temperature square. And on the right, from Friedmann equation, I also have temperature square, because in the Friedmann equation, you remember, right? This is the epoch when the density of matter in the universe is dominated by radiation. And for radiation, I have this relation between temperature and, so my density is temperature to the power 4, yeah? So when I take square root, it gives me 1 over temperature square. That's nice. I can cancel two temperature square in denominator on the left and on the right. And this, well, simplifies a little bit the equation. I have exponent of mass over temperature is equal to some combination of the mass and, well, Newton constant and the cross section, yeah? Then I take logarithm of this, and this gives me T over M is 1 over the logarithm. So I re-express the temperature from this equation, yeah? Good. Is it good like this, or I should better write on the blackboard? You follow, right? I don't appreciate this pre-cooked slides, because, well, when I write it down, I follow myself, I don't do mistakes and so on. So somehow it appears, well, it comes with the rate at which I can digest it, yeah? But, well, you can look at this later if you want. So this is the formula. And what I see here, my temperature of decoupling of this massive analog of neutrinos is more or less the rest energy of the particles divided by this logarithm. And typically this logarithm is a big number, right? Because, well, if I, yeah, what I did here. So it has, this we can do on the blackboard. So logarithm is such a thing that even if something that is under the logarithm is a huge number, I don't know, 10 to the power 10, if I take logarithm of the base 10, then it would be just 10, right? So if it is 100, then it would be, well, whatever, yeah? So it's a slowly growing function. So what I see here is that the temperature, even if this number is huge, I will comment on this notation here, the temperature is sort of 10 times lower than the rest energy, yeah? So it is a self-consistent assumption that I made at the beginning that maybe the particle decouples when it is already non-relativistic, right? And then I confirm, yes, it decouples when it is already non-relativistic. Just in case I use this trick, you see I had Newton constant to the power -1/2, and I replace it with something that is, this has, well, suspiciously, it is called M. So I mean some mass scale. Yeah? I even add here PL for Planck. That's, well, just a side remark. That's a known, for those who do particle physics, that's a famous scale for particle physicists that they would never reach. It is called Planck energy or mass scale. In this system of units that I use, where is it? Why it doesn't work? In this system of units where my H bar is 1, C is 1, the gravitational constant has the dimension of 1 over mass or energy scale square. How do we check this? Let's take this formula, for example. Potential energy is G m square. It's another m, right? So it's divided by r. We have seen the formula like this, yes? So what do I have here? If I write for dimensions, I can write electron volt on the left is equal to this dimension of gravitational constant times m. If I replace m by mc square, I can measure mass in the energy units, right? Because my c is 1. So I have here electron volt square. And for R, of course, it's measured in centimeters. But if I take a combination H bar C, which is 2 times 10 to the -5 electron volt times centimeter, I have a way to convert electron volt into 1 over centimeters. The essence of this conversion is that if you consider photons, right? For photons, I can interchangeably talk about energy of photons or wavelengths of photons, right? So I, being sort of economic, right? I would say, agree that, well, let me talk always about electron volts. Let's forget about wavelengths, right? So then in denominator, I have centimeters, and 1 over centimeter is actually electron volt, right? So I see that my units of the gravitational constants are electron volts, 1 over electron volt square. So it's 1 over energy or mass square, yeah? Because energy and mass is the same. And well, this, I can tell that in general, G is 1 over some mass scale square. And this is called Planck mass, just in case it would be something like, does anybody who goes to particle physics? So particle physicists are gone. There was half of particle physicists here last time, or before last time. So just in case, it is 10 to the 19 giga electron volt or something. Yeah, this is to compare. This is some energy scale that would never be reached on particle colliders, because at the moment, say, LHC works with energies that are 10 tera electron volts, or 10 to the 13 electron volt, or 10 to the 4 GeV, right? This is 10 to the 19. This is way beyond the capabilities of mankind. But it is an interesting scale. It's a scale at which a particle quantum particle will spontaneously form a black hole because it's de Broglie or Compton or whatever wavelengths, characteristic wavelengths is about the size of the black hole horizon. It's just for curiosity, right? So that was a side remark. My replacement of this by, and it's for me, it's handy because I can match the units. I see electron volt to the 4, and Fermi constant is electron volt to the -4, right? So I'm sure that I think my quantity under the logarithm is dimensionless. Okay, so that's my calculation. And then the rest of the calculation is the same as for neutrinos. I know that this massive analog of neutrinos would decouple at this temperature. And since that time, nothing happens to them, to these particles, right? They are only diluted by the expansion of the universe. So at the moment of decoupling, I know their density from this very first formula here. This is my initial density at the moment of decoupling. And then after that, it's only 1 over the volume factor that decreases the density of the universe. So today, the density of this of the particles. Today, the density of these particles would be the difference of the scale factors to the power 3 times the initial density. If I do the calculation, I plug in this formula, it is this formula. And then I can also express the mass or energy density of these particles if I multiply n by the particle mass, right? And then after a bit of reduction, I find this formula. And what is a remarkable thing about this formula, sometimes in particle physics, it goes under the name of WIMP miracle. So somebody was so happy about some peculiarity of this formula that well, he coined the name. This, you see, it doesn't depend on the mass. So whatever is the mass of this massive analog of neutrino, it can make, well, now I plug in the numbers. G Newton I know, T0 is the temperature of the cosmic microwave background today, of the universe today. So I can make all the mass of the universe with these particles if, well, I fix the value of this combination, sigma times V. If I fix it to something like 10 to the minus 25 centimeter cube per second, because it's cross-section time velocity, right? This would give me this magic number 10 to the minus 29 gram per centimeter cube, right? Whatever is the mass, right? This is good for particle physics experiments because, well, they would, if everything would depend on mass, they would need to tune the experiments in a more subtle way. Now, well, it's a challenge, right? So we can formulate a challenge for particle physicists like this. Well, we claim that there is a particle with cross-section like this in nature. Go and find it, right? They can design experiments. They can look for this sort of particle in collisions of other particles and so on. So the whole construction goes under the name of weakly interactive massive particles, or for short, WIMPs. And it's one of the most popular models of dark matter. It's not the only model. I gave it as an example because it was easy to present following this example of neutrinos. But let's say there are many theoreticians upstairs, by the way, who are working on other models of dark matter, but more or less everybody follows the same pattern, right? So if you want to propose a new model of dark matter, you present an argument that this dark matter was perhaps produced in the early universe, and why the universe is full of dark matter today. This is because there is some relic abundance of this dark matter today, just in the right amount to make it, to make all dark matter. So that's the idea of WIMPs, okay? Good, everybody has followed. Now, Later today, I will try to show how, well, can we constrain this, can we test if these WIMPs exist? But to get to some real tests, I need to introduce you some data that we are using, yeah? Let's try to go through some complementary evidence for existence of dark matter from astronomy. Up to now, we have seen only sort of cosmological evidence, right? Let's try to see how does it work in astronomy. I will make a break in 10 minutes, but before this, I would present this. The first evidence is the direct, follow-up on this story of Zwicky. You remember at the introductory lecture, I told that the term dark matter was coined by astronomer Zwicky, and he was studying Coma cluster of galaxies. This is shown on this picture. This every yellow spot here is an elliptical galaxy. So for a reminder, Zwicky was wondering if these galaxies, he hypothesized that these are galaxies, right? Not the clouds in our galaxy, but galaxies like our own. So they are, he made the hypothesis that they are held together by a common force of gravity, yeah? And then it didn't work, the hypothesis, but he told that whatever, perhaps there is some matter that I don't see in the telescopes. And this would be the dark matter. And then, let's try to follow this argument in a little bit more detail. If I imagine that these galaxies, they are held together by the gravity, so then they are perhaps moving in a random way. When we have a system, an isolated self-gravitating system, we know that there is a theorem that applies to this system that it is called virial theorem. Have you seen the virial theorem somewhere? Okay, so the virial theorem tells that a bound state of a self-gravitating or system or whatever system where the forces are potential forces, right? That's the idea. In such situation, the kinetic energy of particles, on occasion this would be galaxies, is equal to half of their potential energy. And the potential energy is this G Newton mm over R. So 1/2 of this would be like this. So what do I see here? Well, sigma is, by the way, the velocity dispersion, right? So instead of mv square, when the motions are random, the convention is people write sigma for velocity dispersion. Now, what can I do? I can make a quick estimate from here. What can I measure in this formula? Well, my particles are galaxies, but it doesn't matter because m small, the mass of particle would cancel on the right and on the left. I can measure, for example, the velocity dispersion of these galaxies. How do I do this? How do I measure velocity in astronomy? We discussed this already.
Redshift.
With the redshift, right? So with the Doppler effect, more precisely, right? It can be redshift, it can be blue shift. Because if something is, especially if something is moving toward me and away from me in a random way. So if I average this red and blue shift over all galaxies in this field, I will see that, some distribution that is maybe Gaussian of some widths, right? And the width of this Gaussian will give me an estimate of the velocity through this Doppler effect, right? I know that delta nu over nu is equal to V over C. And on occasion, this will be V parallel to the line of sight. Yes, that's how, if I measure the shift, the red and blue shift, I would measure velocities. Then I can plug it, so it will be sort of, I can relate sigma to V parallel somehow, right? There will be some numerical factor because I'm measuring only one component, but the motions are three-dimensional, right? So perhaps square root of 3 or something like this is the relation. So this I measure. This I can measure the size of the system. I can measure if I know the distance, right? I know the distance, I know the angular scale of the system. So from geometry calculation, I can measure the size. Then this would give me an estimate of the mass if I express mass from here. And for Coma Galaxy cluster, it would work like this. So what we measure is that the velocity dispersion there is about 1,000 kilometers per second. The size of the system is about megaparsec. Megaparsec is 3 times 10 to the 24 centimeters. So plug in the numbers, I would find that the total mass of this system is about 10 to the 14 or more solar masses. That was the calculation of Zwicky. And then, well, we confirm the fact that, well, the galaxies make a small fraction of this mass. So, well, again, how would we do this? We can estimate the mass of every galaxy by maybe mass of luminous matter in the galaxy, which is mostly stars. We would estimate by summing up the masses of all stars. We can estimate this by, if we know the stellar classification, we know what is the luminosity as a function of mass. Then we would know what, well, we make a hypothesis, what are the abundances of different types of stars in the galaxy. And then we can estimate the total mass of stars, right? So it's a bit sophisticated calculation with some unknowns, right? But still, we are talking here about 2 orders of magnitude mismatch. So whatever our uncertainties of the stellar knowledge of stellar populations in these galaxies, they are not so large to explain this 2 orders of magnitude discrepancy. Okay, so that's how we see the dark matter in galaxy clusters. By the way, as a side comment, if I try to estimate the density of dark matter in this galaxy cluster, I would divide mass by the size cube. It would give me something much more important than 10 to the minus 29. It would give me something like 10 to the minus 26 gram per centimeter cube. Yeah, so it's different from the average density of dark matter in the universe. It is here, something like, well, here I try to be a bit more precise because in the universe we find baryons, we find dark matter. And last time I briefly mentioned that apparently there is some weird type of matter that is described by cosmological constant. But have you seen this in the exercises, by the way? Cosmological constant thing? A little bit, yes. So the amount of dark matter is not precisely 10 to the minus 29 because dark matter does not account for the whole matter in the universe. There is this peculiarity. But anyway, again, we are talking about orders of magnitude. So just in case, galaxy clusters are over densities in the this overall average distribution of matter in the universe, right? And galaxies, of course, are over densities. This is important to note. And this will be a nice and important thing if we want to test the presence of dark matter. We should be aware that around us, the density of dark matter is larger than this 10 to the minus 29, right? This is perhaps helping experiments that would detect this dark matter. Okay, this was directly the calculation of Zwicky. Nowadays, well, some of the matter that was dark for Zwicky is not dark anymore. Let's try to see what does it mean. If I go to X-ray band, I see that the cluster glows in a way that is completely different from the visible band. This is exactly one-to-one match here. So this is the visible band image that is contained in this part of, on the right, it is an X-ray image of the same cluster. And what I see in this X-ray image is that there are apparently even no galaxies in it. Everything is this magenta color, blurred stuff. There are two possibilities. Maybe the telescope is bad, X-ray telescope. This is not the case. So the angular resolution of this X-ray telescope is good to see these all individual galaxies, but they are not there. So it's something else that is glowing in X-rays. And we can understand what it is from a simple calculation like this. I come back to the same virial theorem, but this time let's apply this virial theorem not to galaxy gas, but to real gas. So instead of mass of galaxy, I put mass of proton here. If I do like this, I can also ascribe a temperature to the proton gas that would be maybe present somewhere in this galaxy cluster. So we know that the kinetic energy is equal to 3/2 of the temperature. Yeah. So what should be the temperature of my proton gas that occasionally is found in the galaxy cluster? I I express the temperature from the formula, and then I would find that for a galaxy cluster like Coma, of the mass 10 to the 14 solar masses of the size about 1 megaparsec, the temperature should be some tens of millions of Kelvin. 10 million Kelvin, if I multiply by K Boltzmann, I occasionally expressed it in Kelvin, I don't know why. But if I would forget about Boltzmann constant, temperature is around several kilo-electron volt. So that's why the cluster glows in X-rays. So we now understand what happens. Cluster of galaxies is an overdensity in overall distribution of matter. It creates a gravitational potential well. And then if there is some hydrogen gas flying around across the universe, it would occasionally be trapped by this gravitational potential well, right? So it is accumulating gradually in it. With time, the density of gas, hydrogen gas that falls into potential well grows. As the gas falls into the potential well, the gravitational potential energy is converted into kinetic energy and then ultimately into heat. So the gas heats, right? And starts to glow in X-rays. And then that's what we see. And this is kind of matter that Zwicky didn't see, yeah? Because by simple reason, he didn't have the X-ray telescope that we have nowadays, yeah? So it's a nice lesson. If we want to see dark matter, perhaps we just need the matter that was dark for somebody. Perhaps we just need the right sort of telescope, yeah? Now, did we find the dark matter in galaxy cluster in this way or not? We can try to estimate what is the total mass of this gas, hydrogen gas that resides in X-rays and resides in the galaxy cluster and shines in X-rays. We can look a little bit more precisely at the X-ray data. Let me, we can, yeah. No, I put the whole calculation immediately. So what we can measure for this galaxy, for the gas in the galaxy cluster? What I see in this image is that, of course, I can measure the brightness of emission as a function of distance from the center. Perhaps the brightness goes as the density of the gas, right? So if I take denser gas, there are more hydrogen atoms that would emit photons. So then perhaps the intensity scales with the density, or even with the density square, by the way, because to produce photons, I need to accelerate particles, right? So I need particles bumping one on each other, right? So the intensity goes as density square. Another thing that I can measure is, in fact, in every point here in this image, I can take images at different energies and measure the spectrum of emission. And I can check if the spectrum is, does the spectrum correspond to the spectrum expected for a gas of some temperature, yeah? Then I can measure temperature as a function of distance. And then using these two measurements, I can calculate what is the total mass of gas. I can do even better. I can do a bit of modeling. I don't know if you did you follow the astronomy course? Second year by Frederic. Yes. You see the hydrostatic equilibrium equation for stars. Yes. The answer should be yes. So just a reminder, it's the most important equation that say explains why we exist. Yeah, because we exist because of the sun, and the sun exists because it is in hydrostatic equilibrium. What is hydrostatic equilibrium? In the hydrostatic equilibrium, of course, the sun is a self-gravitating system, right? So the gravity tries to compress the sun, make it collapse. So there is a force of gravity. I write it per unit mass cell, per unit volume, right? So this is G Newton M times the density divided by the distance from the center of the sun or of galaxy cluster. Well, it doesn't matter, yeah. The laws of physics are the same. So the gravity is counteracted by the pressure, right? What matters for the unit volume inside the sun or inside the galaxy cluster is the gradient of pressure, right? Because if the pressure is the same from above and from below, well, the pressure force compensates and nothing resists the gravity. So the pressure from below should be a little bit larger than the pressure from above. So the gradient of pressure should be equal to the this gravity force. And then, yes, for an ideal gas, I have this relation between pressure, density, and temperature. This is the equation of state of ideal gas. If I plug it into this equation, I can rewrite the equation as a differential equation on what? On temperature, right? Then, well, you can check that I can express also the mass from this equation. So I can get an equation for the mass as a function of distance like this. And what do I measure in the right-hand side? I can measure the temperature of the gas and I can measure the density of the gas, right? So then I can measure the mass as a function of distance, right? So I can, well, these X-ray observations are very useful. They give me detailed information on the mass profile of the galaxy cluster. I'm better off than Zwicky. He was using these rough estimates from virial theorem. Here I have detailed knowledge of mass distribution across the galaxy cluster. I can even do more sophisticated thing. I measure the density of the gas as the function of distance, right? I can compare the total mass with the mass of the gas that I can find just like this. I would tell mass of the gas is the integral 4 pi r square times the density of the gas dr, right? So this is my total mass. So then I can check if my gas accounts for most of the mass in the galaxy cluster. And well, people do this systematically, and what they find is still the hot gas in the galaxy cluster does not account for the full mass of the that we find there, right? So there is still a mismatch by a factor of few, let's say. The problem is less severe than for Zwicky, where the discrepancy was some more than order of magnitude. Here, still there is a discrepancy, but well, we have found part of matter which was dark for Zwicky. It's not dark anymore for us. There is something left for to do, yeah? Okay, so this is one astronomical evidence, right? Maybe let's make a break of, 10 minutes? And then we go on with further evidence and then first tests, yeah? So now it's what? It's 10 minutes past 9. Let's come back at 20 past 9. if there are any questions, no. So let's restart. There's still somebody missing, but oh, welcome. Now, so we looked at galaxy clusters. So this is the direct link to the initial, say, discovery of dark matter. Let's look at smaller scales. Let's look at the galaxies, like our own Milky Way. If we, well, the basic fact about the Milky Way is that it is a disk galaxy and it is in overall rotation. So there is a galactic center somewhere 8 kiloparsec from the sun, and the sun, as all other stars, is moving around the galactic center, perhaps over along a Keplerian orbit, in the same way like stars are moving around, planets are moving around the sun, the stars are moving around the center of the galaxy, right? We can use this fact to measure something about mass content of the galaxy. What people do, they measure the velocity of rotation as a function of distance from the center. This is for the picture here on the left is for our own Milky Way. What can we see? So the sun is somewhere, as I told, 8 kiloparsec from the center. And then the velocity of rotation at this position is 230 kilometers per second. So we are moving pretty fast, right? Then we can look at other stars, again, using Doppler effect, or by the way, nowadays there is this Gaia satellite, Gaia telescope that can measure both the the velocity through Doppler effect, and it is called velocity of proper motion. So velocity of motion of stars across the sky. Yeah, it does it to measure distances, by the way, through this parallax effect. Remember we discussed, did we? We did. So it sees this parallax motion along small circles because, well, of the motion of the Earth around the moon, or around the sun, sorry. I'm a bit tired because I was, as I told, I was lecturing yesterday in the evening also. So then, apart from this parallax motion, Gaia can see that these circles that stars make on the sky, they move with time, yeah? This is because there is the velocity of the component of velocity perpendicular to the line of sight. Yeah. So in fact, for most of the brightish stars in the galaxy, Gaia can measure three-dimensional velocity, and it can locate them in 3D space, right? So in fact, this velocity pattern of rotation of Milky Way can be seen in great details nowadays with Gaia, with full 3D velocity measurements. So we extract the velocity of rotation as a function of distance. And this is for the Milky Way. We see it tries to stay at the same level of 230 kilometers per second over a range of distances. Then we can compare it with the theoretical expectation. What is our theoretical expectation? The motion is non-relativistic, certainly, so Newton mechanics applies. Then we can write the Newton law for rotational motion. This is the acceleration, v square over r. So we can express velocity, and this will be the known Keplerian velocity, the same formula as for planets moving around the sun. The important thing about this Keplerian velocity is that, let's say, imagine that we are at the outskirts of the galaxy, beyond the distance of most of the stars and most of matter. What do we expect? The overall mass within the radius stabilizes, yes? And we expect that the behavior should be as 1 over square root of the distance. So sooner or later, we expect this rotation velocity to decrease as 1 over square root. Just for reference, I put here, well, this 1 over square root dependence, not normalized on the rotation velocity at all. Yeah. So what we can notice in this rotation curve of our galaxy is that we are not yet there, not in this regime, even at the distances of about, I don't know, up to 20 kiloparsec, twice the distance of the sun to the galactic center. This is somewhat surprising because we know that, well, again, from Gaia data, for example, we know that the stars in our galaxy are distributed in a sort of exponential way. And while the density of stars decreases exponentially, more or less beyond the solar radius. Yeah, so we are, in a sense, already at the outskirts of the galaxy. And there is not much visible matter at distances beyond the sun. We would expect that just beyond the sun, the rotation curve should start to go as 1 over square root of r, but it does not. We know that the same is valid also for matter that does not reside in stars. Apart from stars, there is also gas in the galactic disk, also outside the galactic disk, but everything seems to be distributed exponentially like this. And for our galaxy, the characteristic scale is actually half the distance of this between the sun and the galactic center. So this is very puzzling. If well, we would assume that matter generally follows the luminous matter, we would expect that the density of matter in the galaxy is already decreasing exponentially at the position of the sun. But if we use this formula, we just plug this simple approximation that the rotation velocity is constant, we see that mass is still growing linearly with the distance. So perhaps we are facing the same phenomenon of dark matter. The luminous matter is constrained to the interior of the galaxy, but the dark matter, by the way, it would be natural because it doesn't like to interact, so it doesn't dissipate energy. It stays in a virialized halo, like in these galaxies of clusters, at larger distances. Yeah, so that's maybe the confirmation of the existence of dark matter that we see in our galaxy. Okay, by the way, the same is true for most of Milky Way-like galaxies. Here, the picture is a sample of rotation curves in many galaxies around us. So a good fraction of them has the same feature. The rotation curve stays constant at large distances. Sometimes there are some peculiarities, but again, this pattern of rotation that I wrote here, it's a toy model, right? We need a galaxy that is sort of, well, non-perturbed in a overall circular motion. Perhaps the dark matter halo is very spherical. Yeah, so my formula is formula that is valid for spherically symmetric distribution of matter. Yeah, there are many galaxies that are not like this because they collide, they well, are distorted, disrupted, and so on. Right. So we should look at overall pattern of rotation velocity on average, not at the peculiarities of some specific galaxies that might be interacting or disrupted or perturbed. Okay, so what was it? Right. So I do a bit more, I give a bit more details for our own galaxy. In our own galaxy, there are these measurements by Gaia and other telescopes that allow us to really map the mass density as a function, mass or as a function of radius. This would be the mass profile of our own galaxy from some publication. It tells us that, let's say, well, this is the black line here is the part of the mass that we can account, well, counting all the visible matter that we have around us. And these colored lines, these are models based on some theoretical template. We see that most of the models predict that at the distance of the sun, we have 50-50 democratic well, redistribution of mass. Half of the mass is of the density is in the form of dark matter, half is visible matter, but soon after, somewhere if we go to larger distances, it is dark matter that dominates the mass, right? In the interior of the galaxy, say below 1 kiloparsec, within 1 kiloparsec distance, it is the visible matter that dominates. So this is one fact to know. And the other fact, the curiosity here is like this. So you notice that the dark matter model that was fitted, it has this NFW. So this is for the 3 persons who proposed first a theoretical template. They derived this theoretical template by running some simulations of galaxy formation. They noticed that in numerical simulations, the dark matter halos of galaxies, they typically follow the same template, right? So it is sort of universal sync. And their fit to their simulations was some specific density profile as a function of radius. It is called Navarro-Frank-White density profile. And this simulation setup tells us that it looks like it is an interpolation between a profile which is 1 over r at small distances, 1 over distance to the center of the galaxy, and it gets to 1 over r cube. There is additional r square at larger distances, right? You see that the curve is gradually getting sort of more flat, right? So if we integrate to infinity, of course, the mass of the galaxy is finite, right? So if we integrate 4 pi r square times this density profile, this would be a finite mass. So the total mass gradually gets to some fixed limit. The interesting thing to note is that close to the galactic center, the density gets higher and higher, yeah? It is a spike in the density of dark matter that is predicted by theory. This is one thing. Then, yeah, maybe another thing that I can extract from this picture is that if I look at the total mass, at the normalization here, the total mass within the solar distance is something like 10 to 11 solar masses. If I divide this mass by the volume, I find the characteristic density scale. That would be about 0.3 giga electron volt per centimeter cube for the dark matter around us. If we make a reference to this previous model of good neutrinos, right? So massive neutrinos. We were talking about particles that are, say, 100 giga electron volt rest energy. So they would be, if I estimate the number density, or maybe 10, well, here I normalized on 10. So they would be something like a particle per every 10 centimeters, yeah, something like this. So there is around us, there is, again, a lot of these particles to catch, right? There is, of course, much more of this relic neutrinos, 100 per centimeter cube, but there is a decent amount of particles if the dark matter is made of WIMPs, there is a decent amount of WIMPs in this room, yeah? That's something to notice. And these WIMPs are moving across the room at some crazy speeds. If we think about what is the typical velocity scale of these particles around us, it would be something like this. We would again use the virial theorem because WIMPs are like this gas in the galaxy clusters. They reside in the gravitational potential well of the galaxy. So looking at the virial theorem, I would make an estimate of the velocity of WIMPs. Occasionally, it gives me the same Keplerian velocity. So it would be about 200 kilometers per second. Then across this room in random directions, because of course WIMPs are not, we are also moving around the galactic center with 200 kilometers per second, but we don't notice this because everything around us is moving with the same velocity as we do, this is because all the molecules in us interact on each other. So we communicate and we try to move coherently, right? It's not that my left arm moves with 200 kilometers per second to the left and the right arm moves to the 200 kilometers per second to the right. But dark matter particles, they don't communicate to each other. So they really move in random directions. They cross this room, in the direction they like, yeah? So it's a nice phenomenon, which is interesting to study, right? So next time we will try to see how people are attempting to catch these dark matter particles in laboratory. But already before this, we can look at another effect, maybe like this. There is a lot of these WIMPs around us here in this room. There is still more of them closer to the center of the galaxy, right? So the concentration of dark matter particles grows and grows according to this Navarro-Frank-White model. There are some alternative models, but let's take this optimistic model. So the density of WIMPs, it grows and grows and grows toward the center of the galaxy. We can imagine that something like these particles start to recouple to normal matter little by little, right? So they were coupled in the early universe when the density was high. So their time before next interaction was smaller than the age of the universe. That's why they were coupled, right? Here, if we go toward the center of the galaxy, surely we can find the distance at which the time before the next interaction of WIMPs will be shorter than the age of the universe. It will be rather small distance, but this happens, right? So somewhere in the center of the galaxy, WIMPs are interacting. And what does it mean they're interacting? There are reactions like this possible. If a WIMP particle or dark matter particle finds another dark matter particle, they would collide and produce, through these weak interactions, they would produce some standard model particles. That can be any particles. Actually, the easiest way is to produce particle pairs so that we don't violate any charge conservation laws. We can produce, for example, a pair of quark and anti-quark. What would happen to this quark and anti-quark? Typically, and it's a pity that there is nobody from particle physics here. But the feature of quarks is that they don't like to be alone. Yeah, they try to hide into bunches of other quarks called hadrons, right? So these quarks would hadronize. Typically, they would produce particles that are made of two quarks, pions. But these particles are unstable. They would decay and produce something that is good for astronomy. They would produce photons. This means that we can somehow see this effect of accumulation of dark matter in the galaxy center, because the galaxy center would glow in photons. Another possibility is that, let's say, dark matter particles colliding, producing pair of electron and positron. This is still easier because the energy of electron and positron would be around the rest energy of dark matter. We are talking about this 100 giga electron volt particles. So it will be a very energetic electron and very energetic positron. They would start to lose energy and again, well, emit photons through, for example, Compton scattering of low energy photons, yeah? So again, we can observe this into telescopes. We can also have the very simple situation when two dark matter particles meet and produce a pair of photons. This is also possible. Maybe yes, maybe not, with some, tricks, because of course we cannot directly produce photons because photons are particles that are produced in electromagnetic radiation. So we need to insert some additional particles in the interaction point, yeah? But anyway, so these are all observable effects, and we can even predict what is the expected luminosity of the center of our galaxy in photons due to this effect. How do we do this? let's try to follow this calculation here. I write the same formula as for the early universe, right? The time before next interaction of any dark matter particle is 1 over the cross-section, velocity, and density, right? For the cross-section and velocity, we have an estimate from the early universe for WIMPs, right? The density we can extract from observations. So in fact, we can predict how often do particles interact at any distance from the galactic center. And we can, if we take, let's say, if we divide the density of particles by the time to the next interaction, that would give us something like the number of interactions per unit volume per unit time. Yeah, by definition, it's, well, this is the rate, the volume interaction rate. It goes, of course, as square of the density because interactions involve two particles, right? And the cross section and velocity go into the numerator. So this is the volume interaction rate. If I'm interested in the rate of energy output per unit volume, this is called volume luminosity, I would multiply by the energy released in every interaction. This would be 2 times the rest energy of the particle here, yeah, because the two dark matter particles disappear in interaction and give energy to the normal particles of the standard model of particle physics. I notice this SM is the standard model, yeah. So this is my predicted volume luminosity. In this Navarro-Frank-White model, it goes as 1 over distance to the galactic center square. So I expect to see a nice extended source in the direction of the center of the galaxy, right? This we can look with the telescopes for this source. Another possibility, by the way, I can also look at what happens locally close to me. If there are dark matter particles interacting at the distance of the sun around us, they would occasionally produce, for example, electron positrons that I can directly catch. If I put a detector somewhere in space, these electrons and positrons would be passing by the detector. I can count them. I can try to see if there are there is a signal of this sort. And well, this is the result. So on the left, it is the device that counts electrons and positrons. I mentioned it already. It is installed at the International Space Station called IMS-02. It's a particle detector like particle detectors in CERN, but it catches cosmic ray particles that pass by, yeah? So what do they see for positrons? This is the spectrum of positrons measured by this detector. And well, they measure some spectrum, has nice shape, right? So the question is there a signal from these dark matter interactions here? Not obvious a priori, right? It's some shape of the signal that, so how would it work? We need to see if we can explain this spectrum of positrons with whatever conventional model of cosmic ray physics, yeah? And then see if the explanation matches the observation or not. If it does not match, we would report an anomaly in the measurements, so, or some excess in the measurements that is unexplained, right? That might be a smoking gun of dark matter. That's what people do, and this is their best fit model. So the conventional model tells us this is this diffuse term that, well, the spectrum, the predicted spectrum of positrons is like this. This predicted spectrum of positrons comes from the fact that there are these cosmic ray protons going through the interstellar medium. They bump into other protons, produce secondary particles, and there are positrons among those secondary particles, right? So if we make a calculation, the prediction would be like this, but the data do not match prediction at all. So this team of AMS-02, it abstractly adds a source term, right? Whatever the source is. Now this source term, their favorite explanation is, of course, the dark matter, because well, everybody is keen to discover the dark matter, yeah? But I can assure you that there are tons of other ideas how this can be explained without involving dark matter. So it's perhaps not yet a smoking gun. Then another device that looks for the dark matter for the signal from this sort of interactions of dark matter is a gamma ray telescope. It is, I also mentioned it already, it is called Fermi Gamma Ray Telescope. The idea here is that if we are talking about WIMPs, these are particles with rest energy about 100 giga electron volt. When they interact, they would produce photons of the energies around 100 giga electron volt. So we need a gamma ray telescope to detect that, right? Then Fermi is a gamma ray telescope in space. It can look in the direction of the galactic center and try to find this bright gamma ray source, which is due to the annihilation of, well, interactions of dark matter. It can even measure this 1/r square brightness profile. Yeah, in principle, the telescope is good enough for this. And then again, when people look in the direction of the galactic center, they see something that they call GV excess, which is unaccounted. Means that, of course, well, this dark matter source is not the only source of gamma rays in our galaxy. But if we try to model all the sources around the galactic center, we still find that there is a space to insert a source with 1/r square profile. And if we measure the spectrum of the source, it will be like this. So in principle, Fermi data are consistent with the presence of a dark matter source there. Yeah, that's called, again, it is called an excess, right? It's not a smoking gun for the dark matter presence, right? Because we are not sure. Maybe there is another source that has similar properties. Yeah. We need perhaps multiple signatures from different experiments that would point to the same type of dark matter. Then we will be starting to talk about, well, identification of the nature of dark matter. So just in case you see that this evidence and this evidence, if we take this as an evidence for dark matter, they are not consistent with each other, right? Because here we are talking about particles that have energies around giga electron volt. Here the excess is at hundreds of giga electron volts. So these positrons produced by this dark matter are not the photons produced by that dark matter, right? That's not good because we cannot, well, we should be economic, right? So it's perhaps should be the same dark matter that produces them. So just to finish, well, in the absence of smoking gun evidence, what people do, say with this Fermi telescope, they tell that, okay, anyway, we can either consider this excess that we see in the galactic center as an evidence for the signal. In this case, we would have a dark matter with the mass, which is, say, some tens of giga electron volt. And remarkably, the cross-section of interaction should be somewhere close to the 10 to the minus 25. Well, this is sigma v, right? Everybody likes this combination because it comes from cosmology. Oops, we have seen this sigma v already. Where was it? Somewhere here in the very naive model of WIMPs. Where was it? Yes. This is here, right? And what we see in Fermi data is exactly what we wanted. So the Fermi data is in fact consistent with the possibility of WIMP dark matter. But then, well, different people testing this, they find that, well, we don't really, well, it is perhaps not the dark matter, because if the dark matter interacts in our galaxy, it should interact in nearby galaxies. And in nearby galaxies, we don't see this nice 1/r square source, right? So they put the limits on the dark matter abundance, which is at this level, that dark matter cross-section. So apparently the data of gamma ray telescopes, they rule out possibility of existence of this WIMP dark matter with rest energy or mass below 100 giga electron volt. That's why I started to talk about 100 GeV from the very beginning, yeah? So that was the last slide, just to mention that, well, there are astronomers trying to catch WIMPs. There are also particle physicists trying to produce these WIMP particles. Well, the idea here is like this. In the center of our galaxy, what happens is that WIMP particle collides with WIMP particles and produces some standard model particles like photons, yeah? Then what can happen in collider experiment is the opposite. When standard model particles collide, they can produce occasionally these WIMPs, right? It will be like neutrinos. We will not detect them, but there will be some missing energy in the collision. They don't observe this, so they do the same. Look at the plots are really comparable. There is even Fermi curve on the left plot. So there is one of the experiments is called Atlas at LHC. They also sort of seem to rule out the possibility of existence of WIMPs with mass lower than 100 giga electron volt, right? So there are different groups of physicists trying to catch these dark matter particles, on occasion WIMPs, in different ways. Yeah. And I will continue with this activity on trying to catch WIMPs next time also, right? Good. So that was all for today. Am I on time? Yeah, we were supposed to end 9:45 or 10. I still have 10 minutes. Huh?
7 minutes.
7 minutes. Cool. Well, I can show you another story then. I skipped the slide because I was trying to not to overflow the time limit. It's a well, permanent confusion for me. Yeah. So maybe, if you have questions to the previous story, ask them, because I will make a sidewalk of 7 minutes now. No. So if I come back to this story of galaxy clusters, I told you that we can see dark matter in several ways in these galaxy clusters. One way is the Zwicky way. We can use the motion of galaxies in the galaxy cluster to measure its mass, right? Then the second way is to use X-ray data to, with assumptions of this hydrostatic equilibrium, to measure the dark matter profile as a function of mass profile as a function of distance, right? There is still one more way to see dark matter in galaxy clusters, and also in galaxies, by the way, if we use the effect that is called gravitational lensing. If you follow the course of astronomy, you surely have seen this, because this is the specialty of Frederic Courban. So the effect is like this. If we look at, this is not COMA, but another galaxy cluster, we look at the galaxy cluster, we see these galaxies, these are elliptical galaxies, the yellowish spots, or sometimes it's perhaps a spiral galaxy, I don't know. So this is like before, but there are some strange defects in the image, right? Do you see these strips here and there? This is because there was somebody who put a teacup on the image, right? And then moved it, and that made scratches on the photographic plate. Yes? Now, these are some real things observed, present in the image. These are the images of galaxies that are behind the galaxy cluster. They are distorted by the effect of gravitational lens, because gravity curves the way of traveling of photons, right? So if we imagine, this is the sketch. If I imagine a source, where is the source? The source P behind a mass concentration, which is a galaxy cluster. The light rays would be curved when they pass next to the mass concentration. So, well, it's exactly, actually, there is an equation that is called lens equation. it's by analogy with the lens equation in optics. There is a lens equation in gravitational lens optics, yeah? So we know that the deflection of light by the gravity is given by this formula. You notice it's always the same combination that appears, g Newton times the mass of the lens divided by d, which is the impact parameter. On occasion, this would be d. Yeah? Perhaps d is this distance here. Yeah, it's like in scattering. Yeah, when we try to scatter a particle on some scattering center, there is an impact parameter. Yeah, so this the deflection angle is given by this formula. It would tell us that if for a coma-like cluster, if the galaxy in the background is at the impact parameter, so it's at the periphery of the cluster image at the distance, this distance about 1 megaparsec, there will be several arcseconds deflection of light. Yeah, this is a measurable effect because the resolution of telescopes is better than this, and this deflection would at minimum it would distort the image of a galaxy. Imagine that I'm looking now not like this, but I'm making a sketch from this side. So this is I'm looking at the galaxy cluster. This is it, right? There was a galaxy here. This deflection would push the galaxy away, yeah, by these 4 arcseconds. Now, if my galaxy is resolved, it is a nice spiral galaxy like this here, yeah. Without distortion, it would be a nice roundish disk galaxy, right? But now my gravitational lens effect, it pushes the galaxy like this. It pushes this part here. It pushes this end of the galaxy here, and this end of the galaxy over there, right? So overall, my galaxy gets distorted like this. It starts to look like stretched in one direction, yeah? That's what we observe here. And you can imagine that by measuring distortion of background galaxies as a function of distance from galaxy center of the galaxy cluster, we can reconstruct the mass profile of the galaxy cluster. Yeah, that's a nice third way of mapping the dark matter in galaxy cluster. Sometimes we can do this also with a galaxy, right? If there is a nice alignment of some galaxy, very massive galaxy, and there are some background galaxies, then, well, we use this effect to map dark matter here and there in different variations. By the way, last year, there was a dedicated space telescope launched. It's called Euclid, that would map the dark matter in more or less a lot of galaxy clusters, galaxies, and in between. So it will map the dark matter over all the large-scale structure of the universe in some direction. You have to make some nice 3D map of dark matter distribution. Using this effect of small distortions of shapes of galaxies here and there, right? That is well, one of the flagship missions of European Space Agency. And there is a group in Geneva working on Euclid data, by the way. Yeah, so that was 7 minutes, even less. I have still 30 seconds left. I present you one more subject. No, well, let's stop here. Any comments, questions? So we make a break of 15 minutes and then with the fresh forces, you are ready to do exercises with Volodymyr.